meeting you. Okay. All right, welcome. Okay, okay. Then, very good, thank you. So good morning, everybody. It's really nice to go on forward now. And I was very happy that we are able to take my computer in action, because that's the idea. I have some programs what I will use for you this course, and then if you are interested on having these programs and using them yourself based on the handouts, they are freely available programs. And this is a really nice program, because with this I can demonstrate a lot of these things, what we have discussed in principle with X-rays and diffraction and so on, because we don't need to know anything what is inside the crystal when the diffraction happens. So this is really pure modeling of this without any knowledge of this. And this is actually a diffractometer simulator. So this simulates the instrument, what we are doing. So in the first course you saw pictures of the instruments and so on, but this is really a mathematical model of that, and you can see this is a very nicely 3D kind of a thing. And the point in here, I will demonstrate which is which. So this is the detector, and the detector can be moved. So, sorry, like this. And we can also move it further, so we can move it out. Sorry, it's a little bit tricky. Out like this. So this is the part of the instrument which reads, the information which is coming from the crystal. And now this part here, in this side, that is the X-ray tube which makes the radiation. And now this is the collimator. This is actually where it mounts. Now the crystal, I will make it bigger, is here. So you can see a thin needle, and that part here is called the goniometer head, into which we actually put the sample. And later on you will learn that the sample is very, very small. So you need that's the reason why you saw microscopic images of these crystals, because they are so small that you can't see them with your eye. So I have to use microscope to select the crystal and then put it in this part. So there is a glass needle, and then there's a loop in that glass needle, and then we attach the crystal in there. So the crystal has to be there on the beam. I will put it on soon. You will see where the beam is. But then you can see here this exotic looking thing here. This is called beam stopper, because only a fraction, a very tiny fraction, will diffract from the crystal. And most of it gets through. And now if you look what is on the other side, so from here, it's the detector. So it would, if there would not be the beam stopper, it would destroy the detector. So we have to stop most of the radiation, and only these ones are diffracted is there. So now I have here a knob, turn the beam on, and now it's difficult for you to see, it's not very nicely visible, but now there is a beam you can see here. This is now a microscopic image. This is a microscope. This is the microscopic image of our crystal. So in here you can see that we have our crystal, and now I will rotate one of the axes. You can see that the crystal is moving inside here. And now the point for us is that in order to record all the reflections, all the information which is coming from these Miller index planes, we have to move the crystal. And that is done by this instrument. So the idea is, first what we have to do is to place the crystal, which is here now, we have to put it exactly in the center. Because only in the center, remember the X-ray beam is something like 100 microns, 0.1, 0.2 millimeters in diameter. And the crystal is sitting inside here. Of course, the choose beside it. So it has to be in the same beam. So let's do this kind of a thing in here, and we can manipulate that ourselves. We can do many things with this, but I just say cheat, and it places that in the center. And now, what is the important point here is that you will see soon, if I rotate any of the axes, like now this, you can see that all the time it remains in the same position. So whatever angles, it's difficult to see, whatever angles we move, even detector of course, or this angle here, that angle. So all these things, it always has to remember, whatever we do, it always has to remain there, in there. But okay, now, when we have the, what is this? What we have the, let's put this distance a little bit closer now, and now make it like this. And what we now want to see is really that if there is any diffraction. Now remember, I discussed you yesterday or mentioned evil sphere. So the evil sphere is a mathematical construct. It's like a virtual ball which is around the crystal. It depends on the wavelength. So I can ask it to be drawn. And now this is the evil sphere of molybdenum radiation. You can see here molybdenum radiation. Now the diameter of this is dependent on the radiation. And then how large or small this evil sphere is, this determines how much and where the reflections are going. That's why we have the detector there. But okay, now I will change the radiation and I will put a copper radiation. You'll see what happens. So it's so much smaller. And there will be a really big impact on that, where the diffraction from the same crystal happens. So now let's define the crystal. So what we have to know, remember there is a unit cell, and now the unit cell can have 7 plus 7, 14 different forms, let's call it like this. And we have to know this in order to see the diffraction, because remember the Miller indices where the refractions are coming are related to the unit cell. And now there is this kind of a default unit cell, and then I accept this, and then something starts to happen. And now I say update this one, and now interesting thing happens. So I will close this down now. Now these red ones, what you see here, are the reflections which are coming. And now if I start to rotate the crystal, and I will rotate this part now here. Sorry. Look. All these are now reflections coming, each of them are from different Miller index plane and represent individual reciprocal lattice point. But now I will increase it to bigger. You can see now there are points. Now these points here, each of them is one reciprocal lattice point. And now, remember I told you that the diffraction happens only when this point sits on the surface of this evil sphere. And now, if you Okay, no. It's difficult now. Now you can see, now it moves, rotates, and each time when the point hits the sphere, the surfaces of the diffraction happens. And this is just diffraction theory. This has nothing to do with the information from the crystal. This is the only unit cell is needed, and then the X-ray beam. Because everything else can be mathematically calculated. So there is no real information in here. It is just a pure mathematical modeling or mathematics. So let's do now a trick. Let me see. I will try to look for this is quite nice. So there's a lot of reflections. And now you can see that point in there is that none of these reflections are hitting in the detector. So they all go somewhere else. So what we have to do, what we have to do is to move our detector so that the beam can be recorded. So now you can see what happens when I move this in here. Now the beam turns green. And in this simulator, the green means that now the detector can read it. And this is what happens in real life. So we have to rotate the crystal and move the detector so that all these points can be, all these reflections can be measured. Now let's see what happens, because now we have copper radiation, and the copper radiation has a longer wavelength. The longer wavelength means that this diameter of this evil sphere is smaller. So you see these diffractions going, really spreading in there. But now what happens, and I change the radiation. In here, we go molybdenum radiation. You see what happened? Only the reflections are going in this direction. And the point is, if I move the detector a bit, I'll just slightly. Now you can see that 3 of these reflections hit the. So when this evil sphere is bigger, the more focused, so more in this direction, all the reflections are appearing. But when we have a copper radiation, they move or happen in completely different direction. And I will try to show this from the top side, like this. Now, so now you can see that the detector is not in a very good position. So when I'm moving it now, you can see that it can read more reflections. And this is what we have to do. But now you can see that in this molybdenum radiation, all reflections are coming like this. So the detector doesn't have to move too much. And this is based on the wavelength. So the diameter of this evil sphere controls the direction of the reflections. But what happens if we change the radiation back to copper? Look what happened. So now it spread so much that previously we have to now move the detector much more in order to see, all the difficult to get, in order to record all the reflections like this. You can see we have to go even somewhere here to do this. And this is why molybdenum radiation and copper radiation are different for the instrument. Because in the instrument, the detector in the copper radiation has to move much more. Okay, and then the final, you can see how they spread. And the final thing really was, let me see here, define crystal. I put it there. Now we have a small unit cell. You can see here 5, 5, 5, and 90, 90, 90. So it's a cubic system, a small cubic system. And now what I've done here, I've asked that the separation of these Miller index planes is 1.2 Ångström. This is the resolution. And now the resolution give us, these are the reciprocal lattice points. So how many reflections there can be from that unit cell. And that depends on the unit cell itself and then the resolution. So I will use the small unit cell now, but increase the resolution to the real one, what we normally use. And that would be, in a case of copper, sorry, 0.8. Look what happened. Nothing else has changed. But I increase the resolution. The resolution means that I have more of these planes because the separation between these planes is the resolution. So the more planes I have, the higher is the resolution. The other way around. So if I have a lot of planes, I have a high resolution. And now you can see what happened. I increased the resolution to 0.8, which is what we aim with the copper radiation. And then you can see the previous number was 305. Now it's 1021. Which means that in here we have 1000 points. And the more we have to collect as much as information as possible in order to get this structure solved. So now I'll make a small change. I will keep the resolution as it is, but I will now change the unit cell slightly. I will just change one axis to 10. Now it will increase, where we have it, volume. And at the same time, because this is constant, it's a bigger unit cell, it can calculate more of these lines or the planes. So it means that we will have more of these points. Let's see what happens when we do this. So now remember 1000. So I will do update. 2000. So this is logical because it doubled. One of the axes was doubled. So now there is 2000 individual things. And now you can see what happens here. We are keeping, nothing is moved, but you can see the red reflections, the number of them is increasing all the time because we will have more of the points here. And more points will hit the surface of the evil sphere. Okay, let's do it again. Let's change this. Let's double that. Now, based on this, we should see double amount of reflections. And now we have 4085. So now increasing the unit cell, but keeping the resolution the same. Of course, we will have more of these planes in there. And then finally, let's change this one too. What is this? 8217. Now we are in a normal scale. So this would be something what we would see in real life. And then you can see the actual idea is this one now combined with the unit cell, we will get 8,000 different reflections, and each of them contain information. And this is actually what we are now going a little bit more further in that sense. And this is just to show you the principal idea about the evil sphere. What happens if I do this? Everything disappears. That evil sphere is now a mathematical construct which is used to describe when the diffraction happens and the reflections appear. But the reciprocal lattice points, which are here, are dependent from the unit cell, and they can be calculated. But now we move slowly. I will now rotate that a bit that you can see. Okay. This is real life. This is what happens. And each of them individual reflections have to be recorded. And what we do, we record its direction, the theta angle, and the intensity. And these are the needed factors then later on. But now we move to the real thing. Let me, sorry. I go out from Windows, and then go to the today's idea. So today we will have actually only one point, one topic to discuss within these two lectures. So we will go for a certain, let's say an hour or something like this, give a break, and then continue with this. Because this is really important issue in understanding what we will see inside crystal. Because you know, you have done, I'm sure, Colt's work and so on about spectroscopy or molecular symmetries and so on and so on. That's very good that you have this. But now when we go to the solid state, we go to the three-dimensional space, something really interesting happens. Some things disappear and some things appear. And this is very important for us to know what is the consequence of this when we are working with the crystal and trying to solve the structure of it. Because it's utmost important. So what it means in real life, it means that we have to know the content of the unit cell, and we have to know the symmetry inside this unit cell. And this means two things. It means the molecular symmetry, and then the solid state symmetry, which is the difference. We have to know the symmetry operations, how the molecules or atoms are organized in this unit cell, because the diffraction comes from there. This is an interesting thing, that the idea we start like climbing to the tree from the top. We are discussing something purely theoretically, but actually all this information is in the data what we get from when we do the measurement. So we use the data to extract all this information. And that's why it's very important when we always say that we have to have a good single crystal, because if the good single crystal, we don't have a good single crystal, we have a bad data, and then we can't get this information. So that is different from the mass spec or NMR, where you can run the experiment. You can always get the spectrum of some kind. It might not be correct, it might be really bad, but you always get something. And here, it's absolutely zero. And that's the beauty and also the beast in that sense, that there is a lot of requirements you have to fill up. And today we will discuss about the real basics on the solid state symmetry. What is the important, what is the meaning? There are a few terms which will be new, which is not, you might have heard them, of course, which are not in the solution or gas phase, because they happen in solid state, and in solid state there is additional things happen. But now, so yes, this is now our set of lectures 5 and 6. It's a symmetry elements and operations. And these are, of course, classical spectroscopy based, but then we will see that we will change gears, and we are not using the spectroscopy's nomenclature for symmetry. We are using different symmetry because these symmetries are embedded in the molecular or the crystallographic symmetries plus something additional more. Okay, so if you think about the molecule, of course, we can see many kind of symmetries. Symmetry you can consider is a property that describes the molecule or an object from a certain point of view, or a certain point, and uses reflections or any of this kind of the mirroring or any kind of other things, can any part of this object to be defined through some operation. And if there is no operations, then there is no symmetry. But this is the actual idea. The symmetry is actually an operation which can describe more than one point. And the idea is that there are many of them, and then we describe them we call them symmetry elements. The symmetry element is very easy to see. It's like a mirror. Mirror is a symmetry element, and nearly all of us will look every morning into a symmetry element. And then we will see something in there which is not us. It's our mirror image. But then the idea, there is not two of me, it's only one, but the other one there is my mirror image. But in the solid state, this kind of a thing can help us, the idea that there are two atoms, but they are related by the mirror symmetry. We only define one because the other one comes from symmetry. We don't have to define. So it helps us in our work. We don't have to define so many things. So the molecular symmetry, which relates to isolated single molecules, in principle can have 5 different symmetry elements. So identity is the same as I am. That it's actually, the idea is that there is no change, and in the spectroscopy it's defined as E. So every molecule has this, of course, because it is by itself. It's identity or whatever you are, nothing else. So you cannot apply to that. There is no symmetry elements. There is no ways of having a copy of yourself through any means. And then this is identity. So that is the lowest possible symmetry element, which means that there is no symmetry element, but it's considered to be a symmetry element also. And then we can have, of course, simply center of symmetry or inversion center, which means that the molecule has a center of symmetry. Any atom of the molecule, identical atom, exists diametrically opposed the center of equal distance. So the idea is that there is easy to imagine that if these would be two atoms and there would be a center, of course there aren't, or that would be now between my fingers, there's now a center of symmetry. So these are related by inversion. And the inversion center should be there in the middle. So it's also quite simple in that sense. If you consider the center of symmetry in our coordinate wise, so x, y, and z becomes minus y minus x minus y minus z. So then we have inversion center of symmetry. Or we can have several kinds of symmetry axes. And the point in there is that the rotation for n folds is called the rotational axis, rotation axis. So it's typically the spectroscopy indicated as C and that small capital or small n in there, a subscript. So it's what this means is 360 divided by n. So it's n is 2, then you rotate is 2 times. So this is 180-degree symmetry in there. Or it could be 3, 4, 5, 6 in principle in the molecular world. But then what we can have a plane of symmetry, a mirror. This is actually what I described to you earlier. So the idea is that there has to be a principal axis, and then the plane is perpendicular to it. So when you are standing like this, then the mirror is it's on the same direction as you are standing, but it's a mirror image of you. And this is quite interesting in that sense, because we are so used to the mirror image that it also helps you a lot in chemistry, just looking yourself in mirror. Because the point is that if you look yourself in the mirror, you are left-handed. And then the point is, this is really surprising, because you will change this thing, because you are left-handed in here. I have really interesting, I have 4 kids, and I have a 50% yield. 2 first ones are right-handed, and 2 later ones are left-handed. So I have it's a racemic mixture in chemistry. But that's the idea. So this is something which you normally don't understand, because you don't see it because you're looking your face. And your face is nearly symmetrical. It's not absolutely symmetrical, but it's nearly symmetrical. But the most surprising thing is really that when you wave your right hand, you wave back with your left hand. And this is really important feature also to understand in symmetries and in solid state. But that's the idea, plane of symmetry and mirror symmetry. And then the idea is that there can be additional symmetries included in there. So what we can do, and it can be done, of course, simply adding up this symmetry. There is this symmetry element and then symmetry element combined. And this kind of a thing we can have, like, it's a rotoreflection axis, improper rotation, it's called SN, and it's a combination of rotation and mirror. And that's that. So these possibilities we have in principle in a molecular symmetry, meaning in a gas pair or solution, but there's no reference to anything else. There's more degrees of freedom because the molecules can be there. They could be, or sevenfold, we can have a heptacyclic structure or whatever, these kind of things in a solution. That's absolutely fine. And the combination, when you combine these things, you will get symmetry operations called point groups. And the point group is a group of symmetries that keep at least one point fixed. So there is always one point. Of course, we have to have a reference point, and from that we reflect these symmetry operations. And that's, of course, it cannot move because when we lose, there is no, it will be blur. That's the idea. And then in 3 dimensions, infinite number of point groups exists. And of course, in theory, you can do this kind of a thing, but they are all can be classified with the several families and so. So some symmetry representations implicitly imply others. So if you have a higher symmetry, the higher symmetry can contain symmetry elements which are of lower symmetry. This is, of course, logical, but not the other way around. Identity cannot contain mirror. That's for sure. But the mirror automatically contains half of it is identity, and the other one is the mirror image. So in this way, that's the idea. So we can have S4 or C4 axis. There has to be also a twofold axis, because the fourfold is higher symmetry, so the twofold is embedded into the same thing. So benzene, it's a very good chemistry example as a molecule, because it has several symmetries. And the idea of the principal axis, if you look perpendicular through the plane of benzene, you can start rotating this. You can rotate this 1, 2, 3, 4, 5, 6 times. In principle, all are there, but the 6 is the highest symmetry because one atom defines 5 others. So if we know a reference point in benzene, and we know that now it's lying, the symmetry elements lying perpendicular for this, we need only one atom, and it creates the rest. And this is sometimes, you will see also when I will show you the programs, it's sometimes surprising when you see a molecule that it looks like it's only one half. And you ask, where is the other half? So you see, for example, it's possible you can see half a benzene ring in your structure in the beginning. And then so what is going on? It can't be, there can't be half a benzene ring. But the point in there, because the other one comes from symmetry, and the program doesn't show you the symmetry. It just shows you the 3 atoms. It's lying, for example, in a mirror plane, that it just sees certain atoms, and the rest comes from symmetry. So that's the simple idea. So, and then the idea is, of course, that any SN axis with odd n is identical to the C axis. So this is with the mirror, of course. So this is the idea that there aren't, like unit cells, there aren't a huge number of possibilities. This is an interesting thing, that life organizes matter. Now I'm speaking in the 3 dimensions, only in a certain way. And there aren't too many, so they're relatively simple to remember. You don't have to remember 500 chemical formulas for days. It's relatively small numbers of important things has to be remembered. And now this is the CERN is used for the name of these, and then you can see here how they name the point groups. So these are the point groups. They're marked like this, that this is a CERN symbol. And here is the operations. I will not go through because this is molecular symmetry, and it's not so concerned about that. But it's the idea that, okay, C1, no symmetry, chiral molecule. And this is important because now we start to see some things which comes from symmetry. So if there is no symmetry, the molecule is chiral because there is no mirror image. And this is an important point for us to understand. And now in this course, it will be, I think, tomorrow, when we go through, it's tomorrow or on Friday, I will go through this structure solution of a chiral molecule. And we don't know the chirality beforehand. And single crystal X-ray diffraction is the only method where you can ab initio determine the chirality. And this comes only from the fact that we know the symmetries inside there. And the symmetry determines then if the molecule is chiral or not. Or in the other way around, chiral molecule determines the symmetry where it can exist. So we can, there is a lot of this crossing information with this tells that this is the case and this tells that this is the case. So if we know this one, we know the other one too. But that's the idea, inversion center, chiral, linear, and so on and so on. But I will not go through this. It's not so important. This is just a continuation. You can see there's a lot of, and then there is some kind of a thing, like pentagonal. This is done on purpose, that's red. In here, in the molecular world, in solution or in the gas state, this is possible. But when we go to now, we go to crystallographic symmetry. So crystallographic symmetry means 3D symmetries. So all these, what we discussed earlier, can exist, except certain things cannot. And the reason for this is that now we are in the solid state, where all the molecules, remember this is the essence of everything, are sitting in an exactly same position in 3 dimensions. So if I'm standing here, my next molecule has to stand there in the same distance, also in there, and there on the back, and in there, also below and up. So in any direction I go, I will see myself exactly as I'm here. And this makes certain things impossible on the symmetry-wise in solid state. So in crystallography, the symmetry operations cannot be combined arbitrarily as others, as we can do in solution. There is no restrictions, but in here, there is. We cannot. And the reason comes from the fact that we are fixed. The molecules are fixed in space. They are ordered in all 3 dimensions. So only a limited number of point groups, which is actually 32, can exist in the crystallographic world, or 3 dimensions. This makes our life, of course, much more easier, because we know that this is not possible, this is possible, this is not possible, and so on. And the combination of allowed symmetry operations and the Pravai lattices, remember we had the Pravai, we have the unit cells. So the point now is that now the symmetry, what we describe, has to exist inside the unit cell. And we have 14 of these unit cells. So we have a combination of 14 times 32, theoretically possible, on all combinations. So if all point groups would occur in all Pravai lattices, that would be the case. But the idea is there that it's not absolutely true. This is, luckily, it's less. So combination of allowed symmetry operations, identity, inversion, mirror plane, rotation, rotor inversion, rotor reflection axis. But now there is this one. You can see maybe on the right-hand corner that if you take certain symmetries and you try to fill space with these symmetries, turns out to be that it's impossible, because it has to be exactly the same repetition. There can't be holes in there. So this actually means this restriction rules out 5- and 8-fold rotations in the solid state, because this will not fill up the 3D volume. So this is the first really crucial information about which kind of symmetry, rotations for example. So they cannot be a 5-fold rotation in the solid state in 3 dimensions. And then the symmetry, crystal symmetry elements do not pass through one point, but they are regularly arranged in space in coordinates, and that is translational symmetry. So that is also an idea that now we can have a symmetry which is not local, but can move. So we can describe something. This is very easy to do. It's easy to understand. So if I would be in a gas phase, I would be all around. And it would be very difficult to pinpoint me where I will be the next time. But if I'm in a solid state, there has to be me beside me. And the point is that if there's me in a certain distance, let's say here, imagine that I'm there. Now, there's a translational symmetry element. So I can be moved like this. It's difficult for me to move myself, but there could be some big guy moving me. And that would be translational movement. And this cannot happen because that is exact. So in theory, you can consider translations also in solution and in a gas phase, but they're completely arbitrary. You don't know which direction it goes. But in here, it's a definition based on the unit cell. And that's the idea. Molecules are sitting in a unit cell in a particular positions, but once we know them, we can have also translational symmetries in there. So that's the idea. So translational symmetry operations are possible. And there are 2 possibilities only. And these are screw axis and Clyde plane. And there will be, I will discuss that a little bit later on, but the point is the screw axis is very easy to describe. And it is actually translational, although it might sound a bit funny just as a name. But the point, what it means this. So when you are translating, you are at the same time rotating. So this is the idea. So this would be a right-handed screw axis, and this would be then left-handed screw axis. And that's the idea. In that sense, the point or the object will move and rotate, or rotate and move at the same time. This is impossible in solution and gas phase in a controlled way. They can do undamble and do whatever things, but you cannot actually say, okay, when I apply this screw axis, then the molecule will sit in there. In the solid state, you can. That's the idea. And then the Clyde plane, which is here, well, the Clyde plane is actually a translational movement on a plane like this. So I'm now gliding, going in this direction. There will be additional symmetry element embedded with this, but this is different. So there is no rotation, it's just movement on this direction, and there is a mirror. So that is the point. So we have the combination of these 7 different symmetry elements. And with these things, we define all the symmetries when it can exist inside the unit cell. And why I emphasize is this, that when we are doing the work, we have to know exactly what is the symmetry in a given unit cell where our molecule is sitting. Because if this is incorrect, then the mathematics again doesn't work. Luckily, there are some ways of handling this and figuring it out and getting information and so on, but that will come later on. So we don't use the CERN flies. We are not use them because they don't have the translational elements in there. So we have to define a new one, and it's called the Hermann-Mauguin HM notation. For this, because this notation tells the symmetry operation, tells which kind of symmetries are there existing. And now let's start going through in this with some examples also. So now identity, the symbol is 1. So if you in crystallography see a symbol 1, it means identity. And there is no symmetry, there is no other than translational symmetry within the lattice. So the next unit cell has the same thing, and the next has, and so on and so on. But within the same unit cell, there is nothing more than this. So you can consider this also that it requires rotation full 130 by itself. It's a one-fold rotation, but of course we don't consider that. So if you rotate, if I rotate 130 degrees, I will be the same. So that's the idea. So the identity, simple minus 1, is equal to nothing in crystallography. So nothing is changed. A chiral molecule or a chiral molecule with chiral packing can crystallize in what we call the space group later on, which is called the P1. And you will learn a little bit later on what the P, or actually you know it already because it's primitive. And the 1 here indicates this. So this is the lowest symmetry possible, a P1, and there is a number. Later on you will learn where the number comes from. And it has only the identity operation. So it's possible. And the point in there is that you have to remember, this is also something interesting, that can a 5-fold molecule crystallize in 3 dimensions? Yes, it can. There is no restrictions that the crystallographic symmetry does not prevent the molecule have an internal molecular symmetry. And it's very easy. You take a cyclopentanyl cation, for example. It's a 5-fold planar molecule with 5-fold symmetry, yes. But there is no symmetry operation to describe the 5-fold. It's something else. And then the molecular symmetry can be higher than the identity. But luckily, this is embedded inside there. So in these symmetry operations, then later on we'll discuss. And then what we speak always, when we speak about objects in the unit cell, we define their position relative to the origin of the unit cell by x, y, and z, the fractional coordinates. So then we have x, y, z. And now, if we do the 300th rotation, it's the same. So do nothing. That's a very simple thing. And now it's marked with 1. So in here, look, a very complex molecule here, a cholesterol molecule, which is chiral molecule, crystallizes in a unit cell where there's only identity. This is absolutely okay. And it has to be so. It has to be that there is no mirror image because this is chiral. If it's optically pure, this has to be emphasized. System changes if you have the mirror image with you. So you have a chiral molecule, you have a left-handed molecule and right-handed molecules. And if there is 50-50 mixture of these things, then it's racemic mixture. And then the situation changes, of course. Or you can have a chiral molecule, like this is now an amino acid. You can see there are 3 amino acids, a glycine here. Now the packing of glycine is chiral. And that the idea is that molecule itself doesn't have to be a chiral if it crystallizes in a chiral space group. So with chiral symmetry, let's call it still like this. So the idea is there that certain things are must, but certain things are possible. So the chiral molecule always, optically pure chiral molecule, always has to crystallize, form the lattice in a unit cell where there is no mirror image. And then if it's a chiral molecule, it can also crystallize, form a crystal, which is chiral, but then there has to be a reason for the chirality, and then it's the packing. For example, there is a helix, a right-handed helix, left-handed helix. Now, what happens then when we have an additional symmetry, the first real symmetry element in there, and then we call the center of symmetry, and its symbol is -1. So the minus here means the center of inversion, a center of symmetry. So the inversion center is a point where there's a motive in the cell, the vector displacement r, in the center where the other motive diametric displacement -r. So x, y, z becomes -x minus y minus z, meaning mirror image. So when this symbol appears in the symmetry of the unit cell, then we know that it's not chiral. So there has to be the mirror image. If it's a chiral molecule, it's a mirror image, okay? Then this also at the same time changes the handedness. If the molecule has a handedness like right hand, then it would become the left hand. That's the idea. And the point in there that enantiomer pure chiral molecule cannot have this symmetry, because symmetry operation would create enantiomorphic pair of it. So that is a very simple statement. Instead, if both enantiomers are crystallized in the same crystal, then it's called a racemate. That's perfectly okay. And fulfills the centrosymmetric condition. So we call this centrosymmetry. So structure is having -1 element in there. It's called centrosymmetric space symmetry operations. And here, this is in the cartoon way how it's in. So we have a coordinate set here. Here we have x, y, z. Now it's the origin here, and then we now have the center of inversion here, and then we have a new atom here, which is -y minus x and minus z. And this is inversion. Here is the D-alanine, left-handed on this side and right-handed on the other side. There is a center of inversion. This is D and this is L. Or if you take a rabbit, then the rabbit goes here upside down. This is very difficult to see that it's chiral, but it's chiral. So if that would be like a left-handed rabbit, then this would be the right-handed rabbit. That's the idea. Biological objects are always chiral. Like I am chiral, all you are chiral, because our sides are not mirror images. Okay, then is the mirror. The mirror is indicated by symbol M. And then in everyday mirror of real object on the other side is equidistant. This is also interesting, but you normally don't actually realize intuitively. But the point is, if you measure your distance from the mirror, from your nose to the mirror image person's nose is exactly within the same distance. But it's very difficult to measure that on that direction because that's just a flat mirror, just an image, mirror image. But that's the idea. So if the molecule contains mirror image, it has to be symmetric. The other half has the same features than the other half. Mirror symmetry in crystallography has same properties, but relates to real objects, like in here. So the point, let's take a mirror image of D-alanine. It's the left-hand side. And now there's a mirror in there, and now it reflects on the other side. Now you can see that this is a typical way of presenting the molecules having a mirror in there, if they are chiral molecules, so left and right, that's the mirror. Or if you have a rabbit, of course, you can easily understand that this is the operation. The point in there is that the operation in principle can be expressed also in a combination of other symmetry operations, but this is not done because we can rotate and then have an inversion of the point. So this could be called as -2, but we don't use this. We don't repeat the same thing by having a new name for this. We just use M for this. So that's the idea. Mirror plane is a simple special case of a two-fold rotor inversion axis, and that's the idea. Now we know what is this, and you can see now here there's a mirror on the x-axis. So x becomes minus, and these remain as y. If we could be having a mirror on the y-axis, then it becomes y, and then the same with z. And in certain more highly symmetrical unit cells, there could be mirror on all of them. So if we would have an orthorhombic system, for example, which accepts 3 mirrors, if we would have a mirror on each of these axes, it would be centrosymmetric because it would create -x minus y minus z. And this is the idea. We use these combinations for that. Okay. Now examples. So here we have a plane. So now this is the base plane, and we add, this is the orange or yellowish. This is the base plane, and here we have, this is our starting or atom, and we place here a plane which is perpendicular to the plane where it's sitting. So there will be a new position in this side, of course. Now, that's a one plane creates a position equidistant from the mirror. Now, if we add another plane, so now there is one, now we put a mirror along this axis, then it will reflect both of these things, of course, in this side. So now each of them will have a new pair, like this. And that was the second mirror. But then we have still one axis here to put in there. Well, if we put here a plane, then it will reflect all these four as additional 4 points. So this means in real life that if we have all three mirrors simultaneously in our structure, one molecule or one atom becomes 8. And that's the beauty of symmetry, because they know each other. Remember, they are packed in real space. You can consider this as an atom or a molecule. It doesn't count. But the point is, there is no diagonal mirror possible. So if you slice this in here, these are not mirror images. So it needs direct angles. So that's the restriction. So that is the idea. The mirror cannot exist when we don't have a direct angle, because with the acute angles, the mirror is not the same. But this is quite intuitive, of course, in that sense. And then we have more symmetry operations. We have rotation axis. I think that will be the last one, and then we give a break. Rotational axis, we have the symbols 2, 3, 4, and 6. Remember now, 1 we don't use because it's the same as itself, and 5 is forbidden. And these are the only possibilities. So in the solid state, you can have rotation 2, 3, 4, or 5 rotation. And it's a very simple description. The idea is 360 divided by n, and n is 2, 3, 4, or 6. And rotation always needs the axis. So it needs the axis around it, what is rotated. So we always agree what is the rotational axis. So the point in there is the idea, the example in here, this is the symmetry element tables. I will discuss that a little bit later on. But the point in here is that this is the idea. So now, we agreed that now the the Z here is rotational axis. So we rotate here this now around this once. So it goes with 180 rotation, is two-fold axis. It goes on the other side of this same axis. Or if we rotate that with the four-fold axis, then it will be 90-degree rotations on that side. So if there is this kind of rotation, then one molecule or atom defines three other ones. And you can see here now, this is the descriptor. So this is the general coordinates, the blue ones, x, y, z, and these are the things. What are these? What the rotation is causing to this. This is mathematically done, and it's already been done 100 years ago. We don't have to think about this. And luckily also the computer program knows all these things. So we don't have to worry about this. How the coordinates will change. But that's the idea. And we'll discuss these notations a little bit more later on. I think we will stop here now, and we will have a break, and then continue with this kind of a thing. The break is now for 5 minutes. Okay, and in 5 minutes, we will be back and continue for the rest of the story. Okay, thank you. Ooh. Okay, thank you. Move to the bait. Oh. Ah. Sorry.